How much Bulldozer can we fit into a single Starship? This is the question I had while I stood watching these vehicles create and then demolish earthworks, while their human operator sat comfortably in an air-conditioned trailer a few hundred feet away. These are Terra Firma's remote-controlled vehicles, an Austin startup that is turning real-world Earth-moving projects into a video game. So now neckbeards can say they work in construction too. And of course, seeing this made me think about the first vehicles we'll use to break ground on the moon. So, how much Bulldozer can we fit into a Starship? The answer is one Caterpillar D11. It's only 10 meters long, and our fairing is 22 meters long, so we could fit 2 in, according to volume, but not according to weight, because the D11 weighs a little over 100 metric tons, and Starship's capacity to low Earth orbit is about 150, and will probably be less for landing on the moon. So we aren't constrained with volume, but we are constrained with mass. So we can only ship one D11 Bulldozer to the moon per launch, as mass is our constraint. And we can say this is about 100 tons. The largest blade we could fit into our fairing to put on this Bulldozer is a 7.2 meter wide universal coal blade, which has a capacity of 65 cubic meters. For one cycle, which is the time to load, push, dump, reverse, and reposition, let's go with 1 minute, which is typical, and this would give us 60 passes an hour, which means we could move roughly 6,240 tons per hour per Starship-sized Bulldozer import. But obviously bulldozers alone aren't enough to develop the moon. For that, we also need loaders and excavators and carts to carry everything. With some finagling, we could probably fit about 2 Cat 350 excavators into a 100-ton Starship, and together these could move about 1,152 tons per hour, much less than our bulldozer metric. But excavators are really meant for digging deep holes and trenches, which will surely be useful, but they aren't optimized for moving bulk mass around. And most of the mass we'll be moving will just be loose regolith that needs to be scooped up to then be turned into materials, and a bulldozer with a ripper works perfectly fine for this job. Except, well, a bulldozer cannot really load this regolith that it collects into a cart for transportation from wherever it's being collected back to wherever it needs to be refined. For that, we probably want to use a loader. I mean, it's in the name. The largest loader we could fit into our Starship would be a Cat 992, which weighs just about as much as the D11, and according to Cat, it would have a cycle time of about 120 per hour, meaning it could move about 4,600 metric tons per hour. This isn't as good as the Dozer, but it's still a lot. The problem with all of this, though, is unloading these large vehicles would be a real pain in the ass. I mean, think about it. How do you get them out of the Starship once it lands? How do you get it into the Starship in the first place? Maybe we can land the Starship sideways and unload it like a cargo plane, and maybe we want to do that for a habitat anyways, but first, it isn't obvious this can be done, or done with a fully loaded ship. Perhaps to land sideways, the ship needs to be almost empty. You know, balancing and all that. Or maybe it can be done, but it's a one-way trip, and you can land sideways, but you can't launch sideways. And in that case, you might want to fill it with life support and stuff so you can turn it into a base, rather than losing an entire rocket just to deliver one vehicle. Or maybe everything goes off without a hitch. It can land and be unloaded and then relaunch perfectly. But then we have to wait however long it takes to develop that version of Starship, whereas the current one is designed to land vertically. So instead of a few large vehicles, why not just send a bunch of smaller vehicles to the moon, which can be unloaded normally, rather than a single giant D11? These smaller vehicles should still be able to move about as much mass as their larger versions, but will be much easier to unload. So not a D11, but a D11 worth of smaller vehicles, a 100-ton fleet of vehicles. But this big vehicle exercise wasn't for nothing. It's still very useful as it gives us some sense of the capacities of this fleet, and that 100 tons of vehicles can move about 6,200 tons of mass in an hour, and can load carts at a rate of about 4,600 tons an hour. And this figure is somewhat akin to what an energy density figure is for batteries. We can say a battery has an energy density of 100 watt-hours a kilogram. So if we needed 1 kilowatt hour worth of energy storage, we know we'd need 10 kilograms of batteries. So we're able to get a sense of what something can do according to its mass. Here we can say we can move 4,600 to 6,200 tons per hour per 100 tons of vehicle, or about 46 to 62 ton-hours per ton. Since that cart loading metric will be our resource inflow bottleneck, let's go with that as our import number. So we know that one 100-ton Starship imported vehicles will give us a resource inflow of about 4,600 tons per hour. And I should also mention that there's other benefits to having many smaller vehicles rather than just a few large ones outside of simplified unloading, namely redundancy. If you have 10 small dozers and 1 brakes, you can still continue operations at 90% capacity. Whereas if you have just 1 giant vehicle and it breaks, your entire operation comes to an abrupt stop until you repair it. And you can repair normal sized vehicles with normal sized tools, whereas with giant vehicles, you typically need giant tools. There are downsides to smaller vehicles though. I mean, you cannot go over larger bumps or move big boulders, and you have to manage a lot more things, so it requires higher computation power and bandwidth, and there's a greater hardware investment per ton moved. Instead of 1 motor per 10 tons, it's 10 motors. But at least in the beginning, I think the benefits of smaller vehicles outweigh the downsides. But of course, at some point we want to phase into giant vehicles, right? I mean, this is the Giant Vehicles on the Moon channel. My videos on that topic are probably why you're even watching this in the first place. And in those videos we talked about how we can make steel on the moon by gathering iron and importing just a little carbon, and how cables and pulleys will be easier to make and maintain than hydraulics, which have a lot more complications in vacuum, and how wheels are probably a better choice over tracks. And so we'll have a design similar to the steam shovels and dozers of old, except powered with electricity using sodium batteries, since sodium can be sourced on the moon. So we lovingly refer to these as sodium shovels. But to make them, we obviously need to have an industry established, which means we need to start with these imported vehicles to make that industry. But the big question is, at which point do we switch over to making these monster moon machines from these imported Earth things? Well, to be honest, I don't really know, but I suppose we can try to get an idea by estimating the mass that needs to be moved over time, starting at the beginning. I suppose one potential early moon moving project will be for a radiation shield around whatever habitat we import. Despite the fact we want to develop the moon with mostly robots, we do probably want a human manned habitat, at least in the beginning. Or at least the government does, and Uncle Sam has the money to afford such a thing. And it can be useful as a lab and workshop for physically testing things on the moon. Let's go big and assume we do use a sideways landed Starship for this habitat. Even if we don't, this is going to give us a higher end number, which will help keep our estimates more conservative. This would require piling roughly 3,000 cubic meters of regolith, about 5,000 tons. A fleet of dozers with rippers should be able to do this job, so we can use the higher 6,200 ton figure, which would mean a Starship should have enough excavation import capacity to build its own shield in about 48 minutes. Of course, this is overly simplified, but it gives us some idea of what we're working with. I mean, even if it takes 72 hours to make, that'd be pretty good. Then I suppose the next step will be to create a landing pad. It's typically understood that for a lander the size of Starship, a landing pad needs to be about 100 meters in diameter, layered with bricks, with the central 50 meters of the pad needing to have 2 layers of bricks. We also need a level surface to make a level landing pad, and the lunar surface isn't level, so we need to lower some areas and raise others to give us a nice flat plane to work on. This process is referred to as cutting and filling, and Jimenez and colleagues determined the cut and fill amount for 3 different polar landing sites, ranging between 45,000 cubic meters and 100,000 cubic meters of regolith that needs to be moved to make a flat and level plane. So we have our pad dimensions and a range for how much moon needs to be moved, but we don't have an exact amount of data for the bricks themselves, so we'll have to employ some assumptions. First, let's assume we're using cast regolith bricks, and let's assume they're pretty big, 25 centimeters thick and half a meter long. Cast basalt's density is 3 grams a cubic centimeter, which means we'll need about 7,360 metric tons of bricks for our 100 meter diameter landing pad. For the cut and fill, let's go with the lowest number in Jimenez's range, since the lunar maria are flatter than the highlands and polar regions. Let's say we need to excavate 40,000 cubic meters to get a nice flat plane for our brick pad. With regolith's density being about 1.6 grams a cubic centimeter, this 40,000 cubic meters would weigh about 64,000 tons. Let's assume 7,360 of those tons go to making the bricks, then we'll need to move a total of 47,360 tons to make this landing pad, which would take our imported fleet about 10.3 machine hours. Then we probably want to build a road leading from that landing pad to our habitat. How much this will cost really depends on its width and length and all that, but by this point I think we can already assume it'll be measured in single-digit hours, if not tens of hours. Alright, well, what's next? I suppose a mass driver, since the reason for developing the moon is to exploit the fact that the moon is usable mass already in orbit. But the problem with this is that to calculate the mass of a mass driver, we need to know its specific design, and we have several types to choose from, and this needs to be an entire video topic on its own. But, well, the thing with this mass driver is we only have to build it once, and then it's done. It's infrastructure, so even if it takes 5 years, which would take a single import worth of vehicles about 200 million tons of material moved according to our 4,600 tons an hour metric, then it's fine. 5 years for a mass driver from a single imported fleet is actually insanely good. It took 10 years to build the Large Hadron Collider and 9 years to build the USS Gerald R. Ford. Although I do understand that's mostly because of bureaucracy, since for some reason on Earth today it takes more time, energy, and money to move a few sheets of paper than a few tons of material. On the moon, we don't have such problems, as there's no NIMBYs or endangered species to cripple our mechanized madness. But obviously, even without bureaucracy, building a mass driver isn't just about moving dirt around. To make stuff, we have to actually turn that regolith into useful things through refining and manufacturing, and that's going to be the real time bottleneck to doing things. Moving the dirt and moving the components made from it is the relatively easy part. And it definitely won't require moving 200 million tons to build a mass driver. The smallest mass driver designs, like the quench gun, require only about 600 tons of mass. But this design employs extremely high forces, like around 1000 Gs, and uses costly materials. On the other end of the spectrum, a mass driver that accelerates loads at just 1 G of force would need to be about 300 kilometers long to reach lunar orbital escape velocity, but could be made of much simpler materials. And since we are measuring in materials moved rather than actual material cost, if we take this 300 kilometer long type of mass driver, we can get a highest end conservative estimate for the material build cost of a mass driver. When I say material build cost, I mean materials moved. We're getting a high end estimate for that. To be clear, this isn't actual cost. A ton of basalt costs a lot less than a ton of gold, but they both require the same amount of machine hours to move. And that's what we're measuring here, machine hours, not real cost in dollars, because we want to know at what point switching to big moon-made machines makes sense. And so we're throwing these big projects at this imported fleet to see where it breaks down. So how much mass would a 300 kilometer long mass driver require to be moved? Well, we can get some rough idea by simply abstracting this mass driver into 300 kilometers of quote-unquote regolith-derived material. So imagine a 300 kilometer wall made of cast regolith blocks. Let's just say it's 5 meters wide and 3 meters tall. This is kind of arbitrary, but I think it's reasonable. It's at least in the ballpark. Cast regolith's density is 3 grams per cubic centimeter, so this entire wall would have a mass of about 13.5 million tons. At 4,600 tons per hour, this would take our single import fleet 2,934 hours, or about 122 days. Shit, that's really good. Okay, well, I mean, I really didn't expect a single imported fleet to be able to accomplish that much. Honestly, I thought it'd barely be able to handle the first radiation shield pile, but well, I guess this is a good example of how intuition can lead you astray and why doing the math is so important. So let's keep going. I mean, we're bound to get to a point where ISRU moon monster machines make sense eventually, right? I don't normally like analyzing past the mass driver stage of things because having a mass driver is so paradigm shifting. I feel like trying to make strong statements about what comes next is like pilgrims planning New York City. But at the same time, it can sometimes be useful to use things like giant space stations and Dyson storms as measuring sticks to get a sense of the scale of things. So let's do that now and be arrogant for argument's sake and look at how much mass we'd need to launch into orbit and therefore move with vehicles to build a Stanford tourist station capable of hosting 10,000 humans. According to Google and a few other sources I checked out, that would require moving about 10 million tons of mass, which would take this single imported fleet about 90 days, using the loader 4,600 ton-hour figure. Whether or not we could actually launch that much mass in a single year using our mass driver or refine it into a Stanford tourist worth of materials is a different question. But okay, we at least know that moving mass around won't be the bottleneck because apparently a single fleet of imported vehicles has the ability to move enough mass in a single year to build 4 Stanford Tauruses. Tauri? Okay, fine. Final boss. O'Neill cylinder. The exact amount of mass required for an O'Neill cylinder was kind of an elusive figure to find, and it seemed to vary a lot depending on your exact design. But one figure that kept cropping up was around 3 billion tons, which would take our imported fleet about 20,000 days. A little over 75 years. So see, we do need to switch to ISRU moon monsters sometime between 4 Stanford tourist stations a year and an O'Neill cylinder. Okay, fine. I admit we might not need to make giant vehicles on the moon. And yes, just landing 75 times would mean we can import enough mass moving machines to move an O'Neill cylinder worth of mass in a year. And yes, by the time we even get to this point, launch costs should have fallen so much that 75 launches shouldn't matter. And yes, we're talking about stuff that's at least 100 years away, probably more, which is like people in the 1920s predicting life in 2025. It's basically pointless from a practical standpoint. So fine, whatever. You win, pedantically logical voice inside my head. I should have done this math long ago. But I won't pretend like I'm not a little disappointed. I mean, I really wanted to see giant bucket chain excavators on the moon. Of course, this relies on Starship or another heavy lift rocket being able to deliver double or triple digit tonnage to the lunar surface, and we haven't accounted for vehicle upkeep, breakdown and repair costs, the need for spare parts and charging times, or the fact that due to the long lunar night, they might only be able to operate for 50% of the time. But look, regarding Starship, I think that cat's out of the bag at this point. Even if it isn't SpaceX specifically, someone is going to build a ship capable of delivering something within the ballpark of Starship's goals. But even if that never happens, and we're forever stuck using New Glenn's 3-ton to the lunar surface, well, with just 10 landings, we'll still have 30 tons capable of moving a Stanford Taurus's worth of mass in just a little over a year.
Simply too good.
I guess the good news is we don't need to build something as grand as a giant bucket chain on the moon before getting to Stanford Taurus-sized stuff. We don't need to spend time and energy figuring out ISRU vehicle designs and setting up their manufacturing lines. I don't mean to suggest that things are now simple. We still need lots of development before getting to Stanford Taurus level stuff, and a mass driver is no joke. But this does seem to lower at least one barrier, and I suppose it sort of makes sense if we think about how much 10 million tons of stuff actually is and visualize it and compare it to Earth mining operations. If we excavated a square pit 3 meters deep on the moon, then for a Stanford Taurus 10 million tons, the sides of that square would be 1.44 kilometers in length. So this quite shallow pit mine would have a surface area of 2.08 square kilometers or 208 hectares. If we excavate 10 meters deep, then the side lengths only need to be about 800 meters, a surface area of 63 hectares. And for pit mines, 10 meters deep is still relatively shallow. To put this into perspective, the Hambach mine in Germany is 500 meters deep at its lowest point and covers an area of 43.8 square kilometers or 4,380 hectares. Enough material for roughly 2,000 to 3,500 Stanford Tauri. of 10 million tons each, assuming an average depth of 300 meters. Okay, sure, the Hambach mine is exceptionally large, but the point is that most earth coring operations are much larger and deeper than what it would take to make a mass driver or Stanford tourist station. But wait, won't we still want one or two larger vehicles to move big boulders and stuff? Well, everything on the moon weighs 1/6 of what it does on Earth, so a 600 kilogram boulder is going to weigh just 100 kilograms on the moon. Well, technically it would still be 600 kilograms, but it would take the amount of energy required to move a 100 kilogram object on Earth to move a 600 kilogram boulder on the moon, if that makes sense. And we can use other methods to handle these big boulders that need to be removed other than big vehicles, such as nails, or an oxygen lance, or just a nice oxygen-based explosive. So there are ways around needing big vehicles on the moon. But now the question is, just because we don't need big vehicles, why does that mean they need to be imported? Aren't these two different things? Isn't there still an advantage to making these smaller vehicles on the moon? Well, remember, the main reason we're going with smaller vehicles is for the ease of unloading them when we import them. And if it was the case that these first few batches of imported vehicles were only enough for the first few tasks involved in developing the moon, and we therefore needed to scale our vehicles significantly to do the larger things, then of course it would make sense to switch to making vehicles on the moon, likely small at first and then big. But as we've just figured out, this really isn't the case, as those first few batches of vehicles should be enough to last you until even the much larger, later stage stuff, which was totally surprising to me. But now you might be thinking, well, if many smaller vehicles are better than a few large ones, why don't we use lots of smaller vehicles and mining operations here on Earth today? Surely the redundancy and ease of transportation and repair benefits would apply here as well, yet we use very large equipment. Well, yeah, I sort of struggled with this question as well. I mean, again, I made 3 long videos on large vehicles on the moon, but what I failed to account for was the size and scope of the operation at hand. That's where I just assumed things. It's sort of like semi-trucks exist, and they're used on Earth all the time, and we like semi-trucks, we think they're cool. And we're looking at starting a restaurant business, so we need a vehicle to get groceries from the local market to supply this business. Do we immediately opt to purchase a $250,000 semi-truck to supply this one restaurant with food? Or do we just use our $20,000 car, which also gets better gas mileage? Well, that depends on how much supplies this restaurant needs. And here we just did the math and found that we probably won't need a semi-truck worth of transportation capacity until we have at least 10 restaurants in our chain. We probably won't need giant lunar-made vehicles until we get to the range somewhere between 4 Stanford Tauruses and an O'Neill cylinder. So this is not an argument that big vehicles are bad or small vehicles are better. It's just an argument that big vehicles are total overkill for anything we'll be doing on the moon, at least for a while. And that argument that, well, we use big mining equipment here on Earth is like saying, well, Walmart uses semi-trucks in its transportation fleet, so shouldn't we copy their model for our restaurant business? Well, yeah, once our restaurant empire gets Walmart-sized, but until then, we can just use a regular car, and then maybe get a company van, and then maybe one day upgrade to a full-sized semi-truck. Of course, they'll break down and need repairs from spare parts. They won't last 1,000 years. But how many will they need? I mean, if they completely broke down and vaporized into dust once a year, then all it would take is 1 import a year to replace them. I mean, it's kind of ridiculous to favor ISRU when you think about this and compare it to the upfront investment it will take to create vehicles on the moon, from the R&D to the establishment of manufacturing lines. And consider that the Earth imported vehicles will benefit from being made of materials produced from our hyper advanced and scaled 4,000-year-old advanced alloy and composite making globe spanning metallurgical and material industries, the alloy advantage. This also applies to the vehicle's hardware, batteries, motors, and electronics. If we can land double or triple digits on the moon, then we don't need to worry so much about weight and can break from tradition and consider using materials that would make JPL scientists jizz in their pants, like high-strength steel alloys, and design the vehicles to be closer to military machines than fragile, lightweight scientific instruments, perfect for our war against extinction. So we can use strong alloys according to robust designs, thus greatly lowering the frequency of repairs and the need to import replacement parts. Whereas with lunar-made things, we're going to be limited to more crude materials, cast regolith and iron and steel. Now, normally we do opt to use these cruder moon materials because they're perfectly fine for most things, and they're so much cheaper than importing, which makes them great for scaling. But here we're talking about so much work for so relatively few vehicles that are needed. 100 tons being able to move 10 to 50 million tons a year, it just doesn't really seem worth it when we don't have a need to scale that much. Now don't get me wrong, ISRU is still king in general, even with Starship-sized capabilities. Solar cells, for example, you can import between 8 and 40 megawatts, depending on panel design, but about 20 megawatts is a realistic figure per Starship import. But to launch that Stanford Taurus 10 million tons a year using a 50% efficient mass driver, we will need about 3.6 gigawatts of electricity generation capacity, which, if importing solar cells, would require about 180 Starship lunar landings to import that amount of solar cells. Needing to launch 9 Starships per lunar landing, 8 of those for orbital refueling, that's 1,620 launches total. And this is just for the panels, not the grid, which would include all the cables and capacitors and batteries and MPPTs and inverters and everything else we might need. So ISRU totally makes sense here, even with Starship's insane capacity. And it obviously makes sense for construction materials as well. But it apparently doesn't that much for vehicles, just because the vehicles can do so much. So does this then mean all those videos I made on giant moon machines were wrong? Well, I prefer the term less accurate, since admitting I was wrong about something would be way too hard on my fragile YouTuber ego. But even if I was wrong, hypothetically, this whole analyzing the future stuff is kind of hard, and you have to be willing to be wrong to make progress in anything. So it's okay for you to admit that you were wrong in your interpretation of my past videos, and I can admit that maybe I could have made them even more right than they already are. But don't worry, I'm not going to take them down because I still think there's a lot of strong ideas and valuable information in them, even if the size of the vehicles portrayed is less right than those in this video. However, there is one exception to this entire ISRU imported vehicles argument: carts. Our vehicle's mass moving capacity, those 4,600 and 6,200 tons moved per hour figures, are based on their cycle times, right? Which we determined to be between 30 seconds and 1 minute based on official manufacturer data. But this doesn't work if your vehicles have to travel 2 kilometers from one end of the mine to the other to drop off their loads, and that manufacturer cycle data has the implicit context of these vehicles working in concert with dump trucks and stuff, or traveling short distances on job sites. So we need to employ the use of carts, or wagons, or hoppers, or whatever you want to call them, along with our dozers, and loaders, and excavators. And here we probably want to make them on the moon for 2 reasons. The first is that we want a lot of them. We want to scale them to match the capacity of our vehicles, so we can have a constant flow and travel time doesn't become the major bottleneck. The second reason ISRU makes sense here is that lunar sourced materials are more than enough for carts. Look at this cheap $30 cart that I think is made from aluminum or maybe plastic. It can carry 30 kilograms or 66 pounds. On the moon, it could carry 180 kilograms or about 400 pounds. We don't even need metal to make carts. Look at this medieval mine cart made entirely out of wood. Can you imagine it being made of regolith instead? Just imagine sintering or casting 5 boards that fit together like puzzle pieces. Casting 2 rods, 4 wheels and a few brackets, and voila, you've got a cart that can be assembled using a robot arm. Import a prime mover, string together 10 of these, and you've got yourself a mine train. Well, I'd say this has been fun getting all my dreams for giant vehicles on the moon crushed, but it hasn't. I hope the realization that a bunch of smaller vehicles working together can make giant space stations just as good if not better than a few giant vehicles is motivating to all you short people watching this. I don't know, maybe it'll inspire you to go conquer Europe or something. And thanks to Terra Firma for the inspiration for this video. If you're too short to work in construction, well, thanks to them, you now might just have a chance. I mean, that is if you can reach the controller. If you appreciate this content and want to help me make more of it and help me make it be more better, then consider becoming a patron or channel member. I do make all of these animations myself, and I'd like to be able to upgrade my hardware and purchase some professional assets, so your money will go towards that, and of course towards furthering lunar development research and education via this channel. For as low as $3 a month, you'll get access to exclusive videos, early releases, the Discord channel, and I'll even put your name on screen at the end of videos. Alright, thanks for watching. As always, thanks a trillion to the current patron and channel members. You guys are amazing. I'll see y'all soon. Bye.